Pokémon Gen 1, the game that started one of the biggest video game franchises in the world. And one of the key reasons why it was so successful is that it was somehow able to cram a giant, sprawling adventure into a highly restricted handheld gaming device. A huge open world in the palm of your hand. I am talking, of course, about our beloved Kanto region. But how was this possible? Today I'm gonna show you exactly how Gen 1 stores its map data. And what better way to understand and appreciate the miracle of Gen 1 than to perform a miracle of ourselves. We are going to recreate Kanto on another highly restrained platform using the same techniques. My name is Christian, people call me the Lazy Devs Professor. A world of dreams and adventures with Pokémon awaits. Let's go! Yes, so there are at least 3 things about Pokémon Gen 1 that always made me wonder what is going on under the hood. First, Kanto is huge. If you stitch it all together, you'll create a map that is at least 5,000 times 5,000 pixels in size. It will take like 2 minutes to traverse from one edge to another. This is way bigger than other comparable Game Boy titles like Link's Awakening or Mystic Quest. But secondly, if you compare the maps like this, you'll spot some interesting differences. Link's Awakening has a perfectly rectangular map built out of individual screens. It's easy to imagine how Link's Awakening stores its map. It probably saves individual screens, and you can build the overworld by assembling them into a grid, like a jigsaw puzzle. In comparison, Kanto is comprised of individual towns connected by routes. There are huge holes in between. It seems like Kanto must be assembled somewhat differently, but it's not clear how. And the reason why it's not clear is because of the third and most perplexing reason. Kanto is perfectly continuous. You can walk from one side to the other without encountering any visible seam or break. You see, in something like Link's Awakening, the map is actually static and the character is moving around on the screen. And when you approach the edge, the map will scroll and that screen will become static again. You could say like the overworld in something like Link's Awakening is built out of individual rooms. Now, not all Zelda and Zelda-like games are like this. For example, A Link to the Past or Secret of Mana also have a map system that scrolls together with your character. But in those games, almost always, eventually you will hit a spot where the scrolling stops and you can approach the edge of the screen, which will trigger a transition to the next map over. So you can also imagine how maybe, these games store just bigger maps and then those maps are linked together on the edges. And in some games, like A Link to the Past, those bigger maps actually even fit together perfectly like a jigsaw puzzle once more, creating this huge cohesive world. Very satisfying, extremely based. But this is not strictly necessary, and games like Secret of Mana are just a bunch of loosely connected maps floating in space. But then there is Kanto, and Kanto is neither of those. No matter where you are, the map will always scroll underneath your character. You will never encounter an edge anywhere, creating this mesmerizing illusion of one huge world. It can be hard to wrap your head around how this is all stored internally. Even if you do enter a space that is almost certainly a separate map, like a room or even an elevator, the map will always scroll as you move. They really went all in on this scrolling thing. Now, to be fair, the map is not entirely continuous. All of Kanto is peppered with these gate buildings or caves that could potentially hide a seam. Mask the place where 2 maps are stitched together, right? But you can still do incredibly long, uninterrupted trips. You can go all the way from the Seafoam Islands to the Pokémon League reception gate. So either they put like 3 towns and 4 routes into one huge map, or there is some kind of clever, even better hidden way on how those maps were stitched together. And yeah, as a player of those games, this might not seem so special. But when you start making your own games and you are faced with creating your own system to manage these types of maps, you start looking into how other devs did it before. After all, there is no reason to reinvent the wheel. And from all of the games that I'm familiar with, Pokémon Gen 1 stands out as the one that always left me a little bit dumbfounded. I decided to investigate, and this is what I found. Luckily for us, the entire game has been disassembled and we can just look at the source code. If you browse the repository of the disassembly project, you realize that yes, indeed, the overworld does in fact consist of smaller maps. The disassembly stores them in those BLK files, and this is what Pallet Town looks like. So first, let's dig into how this is encoded. If you open Palette-Town BLK in a text editor, you just get gibberish. That's because this is a binary file, meaning it's just a long stream of zeros and ones. Okay, so this is a bit confusing because technically every file on your computer is just a stream of zeros and ones. So in a text file, for example, this stream of zeros and ones can be broken up into chunks of 8 bits each called bytes. Each byte can encode a number from 0 to 255. And this number can be then interpreted as a text character using a lookup table like the ASCII table. When we talk about binary files, we mean files where those bytes are not meant to be interpreted as characters. Instead, they're supposed to be read as the actual numbers that they represent. That is why if you try to encode them as characters, you just get gibberish. So instead, it is a better idea to look at the map of Palette-Town with a hex editor. If we do that, we realize that the game somehow needs only 90 numbers, 90 bytes, to draw all of Palette-Town. This is strange. It should be way more. You see, this is the tileset that is used to draw all of the overworld of Kanto. It consists of small 8x8 pixel tiles. The map of Palette-Town is 40 of those tiles across and 36 of those tiles tall. This means we're talking about a whopping 1,440 tiles. But instead of encoding this into 1,440 numbers, the game somehow only needs 90? How is that possible? And here is our first trick. Yes, the game uses something called the meta tiles. If you pay close attention, you'll realize that the game actually operates in a much coarser 16x16 pixel grid. The game always takes 4 of the small 8x8 tiles and combines them to bigger 16x16 tiles. This is the size of the character, for example, and all of the NPCs, and it is also the grid in which we are moving through the world. This is a common setup for a lot of 8-bit top-down games and something I discussed in my previous video about Zelda. Except something still doesn't quite add up. If the game was encoding the maps in 16x16 pixels meta tiles, we would still need 360 numbers to encode Palette-Town, but we have only 90. And here is the real trick of Pokémon Gen 1. The real trick is that this game uses even bigger meta tiles. It always bundles 16 of the small tiles together to big 32x32 pixel blocks. And this is how it's able to encode relatively huge maps with just very few numbers. Now before we move on, let's just get the terminology straight, just so there's no confusion as we move on. For the rest of the video, I shall call the small 8x8 pixel tiles tiles. I will call the bigger, the gameplay relevant 16x16 meta tiles squares, and I will call the huge 32x32 pixel meta tiles blocks. And all of the blocks that the map file refers to need to be stored in so-called block sets. You can find them under GFX block sets. The block set for Palette-Town is called overworld.bst, and it's another binary file. It consists of 128 blocks, and each block is just a sequence of 16 bytes. And the bytes refer to the tile numbers going through the block line by line from left to right. Altogether, it's just a big, huge sequence of like 2048 numbers. That's a lot of numbers, but as the name suggests, this block set is used for every map in the overworld, so you get a lot of mileage out of it. Armed with this knowledge, we can potentially start decoding all of the map data. But back to the original question, how does Pokémon put all those small maps together into one big map? How does it know how to attach those maps together? For this, we need to look into data maps headers. Each map has some additional information stored in a map header here. The disassembly project has put all this information into regular human-readable text files. If we open palette-town.asm in a text editor, we will see the name of the map, which block set it is using, and which other maps it is connected to. Each map can be potentially connected to 4 other maps in the north, south, east, and west. So Palette-Town here is connected to Route 1 in the north and Route 21 in the south. And this is how the game stitches all of the maps together. I found it quite surprising at first. It never occurred to me that the system would be so simple. I would never try to attempt something like this myself. I would be constantly worried about all the different map layouts that wouldn't be possible with this system. For example, what if you have like a long vertical map that is connected to 2 other maps on the east side to make like a C shape? It seems like this wouldn't be possible because you can't have 2 maps connected to one side. Except if you look at it, Kanto actually has such a map, and it works just fine. The big bicycle route, Route 17, forms a C shape. It's connected to Route 16 in the north and Route 18 in the south. Turns out I was just overthinking it. There's probably a lesson here. Probably better to have like a simple system and work with the limitations. Never let the perfect be the enemy of the good. Okay, but there is one final mystery to solve here. If we open the header file of Route 1, we will see that Route 1 is connected to Viridian City in the north. But Viridian City is a big map, 20 blocks across, while Route 1 is only 10 blocks wide. So how do they make sure that those two maps align correctly? Well, if you look closely at the map header, you will see that each connection is followed by a number. It is -5 on the connection to Viridian City, meaning that Viridian City is offset by 5 blocks to the left compared to Route 1. And that is really all we need to assemble all those small maps into one huge map. Except obviously that's not what's happening here. There's just no way this huge gigantic map would fit all at once into the Game Boy's measly RAM. The Game Boy's VRAM can only store like 32 times 32 tiles for the background, so that's not even enough to cover all of Pallet Town. Instead, the game does what a lot of games of its time are doing. It draws in the map line by line into VRAM as you are moving. Using the VRAM viewer on an emulator like BGB, we can see what this looks like. At any given point, the game already has enough of the map in VRAM to fill the entire screen. If you want to move, for example, to the right, the game will quickly load in a thin strip of tiles on the right edge of the screen, just enough to scroll by 16 pixels. And this is happening every single time you take a step. It's like that scene from Wallace and Gromit where Gromit is laying down the tracks in front of the moving train. That's what the game is doing. It's laying down the tiles as you're moving around. And presumably this is also where the stitching happens. Once you arrive at the edge of the map, the game will check if the current map is connected to another map on this edge and will start reading blocks from that other connected map. And if there's no connected map, the game will instead show a default border block. Ever notice that when you walk to the edge of Pallet Town, it seems like the entire town is surrounded by a creepy, unsettling expanse of tall grass? Yeah, this is just the game filling in the edge of the map with a default border block. So far, so good. So this was the theory. Now, let us put this theory into practice and let us recreate the entirety of Kanto in a different engine. Personally, I love Pico-8, but one of the downsides of Pico-8 is that its built-in map system can only support really small maps. Using the built-in map editor, you can really only draw maps of like 128 times 64 tiles. That's barely enough to cover Pallet Town, and it only works like if you sacrifice half of the sprite sheet. Yikes. But perhaps we can get around this limitation by using the very same techniques that Gen 1 is using. But before we get into coding, a word from our sponsor, which is you! Yes, this channel is supported by our wonderful audience over at Ko-fi.com. Thank you everybody for your support, and if you other people out there also want to support bespoke game dev content, the address to do so is Ko-fi.com/lazydevs. Or if you aren't ready for that commitment, just give this channel a little subscriber Rudy. Let the algorithm know that you want more of this. So back to recreating Kanto. We want to get all of this data inside of Pico-8, and that's not an easy task. Pico-8 by itself cannot really read binary files. So we need to turn to Pico-8's younger, bigger, and hotter brother, Picotron. Picotron is a fantasy workstation, and all of the Pico-8 community is still wondering how best to utilize Picotron. Well, it's fantastic for something like this. Check this out.
Reading Kanto data.
First, let us get the sprite sheet into Picotron, and Picotron has a great new tool for that. In the graphics editor, you can simply choose Import Sprite Sheet. You can drag and drop a PNG onto this, set the tile width and height to 8, and slice and dice. Boom! We are ready to go. Next, let's read in the block set. The contents of the current project, also known cart, are always stored in this RAM folder here under cart. I can simply drag and drop overworld BST into this folder, and bam! It just has become part of this project, part of this cart. And I'm gonna save this as Kanto. Okay, so the block file is now part of the project, but we still need to actually read it out. Going over to the code editor, I can write something like this. This will read all of the contents of the file overworld.bst into this variable block data, and it will store it as a string. Yes, all of the 128 blocks, all of those 2000 bytes are now stored into a single string. So yes, the numbers are interpreted as characters, but we can turn them back from characters into numbers using a function called ORD. Look, I can take the first character from the string like this, I can turn it into a number, and I can print that number to the screen. And yeah, look at this. The first number is the number 10. So now we can use loops to loop the first 60 numbers and print them on the screen in a grid. For this, we need to shift everything to the draw function. We need to set up nested loops for the x and y coordinate. We will do a setup like this a lot in this project, and whenever this happens, it's important to remember that the outer loop is supposed to be y and the inner loop is supposed to be x. It is easy to get it backwards because usually x goes first. For this quick and easy example, I'm just using a simple local variable I to keep track which number we're reading next from the string. I'm also spacing those numbers 16 pixels apart so we can see them a little bit better. So we're going to run this, and yes, these are the numbers that represent the tiles of the first block. All we need to do now is, instead of writing the numbers on the screen, we're going to feed them into the sprite function, and we're going to reduce the spacing down to just 8 pixels, and bam! We got our first block on the screen. That's cool! It seems to be some part of the house, I guess? So this is the proof of concept. Now let's load in all of the blocks and organize them into a table for easier access. Let's put this nested loop system aside and let's create a simpler loop that just reads in 60 numbers and dumps them into a local temporary table. Let's call that table myBlock. And then we're just going to take this loop and wrap this in another loop that just repeats this process 128 times. And every time we go through this loop, we're just going to add the contents of the myBlock table to a larger global table called blockset. Yes, I'm incredibly creative when it comes to naming. Instead of using a simple counter, I'm using this little bit of math to determine which character we're supposed to read in next from the string. J counts the blocks that we're reading, and I counts the tiles within a block. Also, this loop starts with 1 instead of 0 to account for the fact that tables and also the numbers of the characters in a string in Lua start with 1 instead of 0, and this is also something that will come up a lot throughout this project. And now we can take back those old nested loops and turn them into a function that will take in a table that encodes a block and will draw it to the screen. It's very important to remove the ORD function from here because we're actually doing this above here when we read in the block data. Alright, so this is our function. Let's see if we can use this to draw the first 10 blocks to the screen. I had to fix some bugs here. I forgot to make those parameters actually control the positioning of the block, but now look at this. Yes! More! We can wrap this for loop into another for loop to draw the entire block set. Look how delicious this is. We have so many blocks, we can't even put them all on the screen. I think we can put a big fat checkbox on this first step. Alright, time to read in some map files. Let's put Palette Town to the screen. I am going to create a new folder in our RAM directory, and I'm going to call it PK Maps. Because there's already a map folder in there. That is a different map system. That's the built-in Picotron system. We don't want to get those two confused. And now I'm going to go into this folder and I'm going to drop in paletetown.blk. Alright, and now we can read in the data from this file the same way we read it from the block set. I'm going to save this, I'm going to run this, and we see nothing. I mean, we read in the data, but how do we put the map on the screen? If you think about this data is just a long stream of numbers. We need to know where to put in the line breaks to turn the stream into a grid. We need to actually know how wide and tall it's supposed to be. In fact, if you think about this, we're going to need actually a lot more information about each map. Remember, we need to store in, what the neighbors of this map are, what the border block is, and so forth. So let's change this myMap object that we created here to hold in all this extra information. For now, we're just going to add a width and a height property, and we're going to store all the blocks that actually make up the map in a dedicated blocks property. And then we can just change the loops in our draw function to just loop through the map and draw it to the screen like this. Since all of the blocks that we're ever going to draw will come from the same block set anyway, I changed this draw block function to accept just an index, and it will grab the block from the block set by its own. This will make the function call up here a little bit less convoluted. And here it's very important to add the 1 to the block number because, again, in Lua, the arrays, the tables start with 1. We're going to save this, we're going to run this, and chewy, we're home. This is where it all began, our beloved Pallet Town, just as we remember it. So now that we can load in one map, let's load in all of the maps! I am going to copy all of the BLK files that make up the overworld into our PK map directory. This includes 10 towns and all of the routes except Route 23. Route 23 is a little bit special. We're going to leave it out. I'm going to talk about this a little bit later. If you did everything correctly, you should have 34 files in this folder. Okay, so we have tons of maps now, but how are we going to get the width and height of those maps? Well, I have bad news. This information is a little bit buried in the repository. You can find the width and height in a file called map_constant.asm in the constants directory. It's a messy file with tons of additional data that we aren't actually interested in. We could parse this file automatically to extract just the data that we need, but I figured it would be worth the effort. And it's the same thing with the number of the border block that is supposed to show up outside of the map. This data is spread all across those ASM files inside the data maps object folder. And we would need to parse all of those files to just extract one number each. I decided to just manually assemble the data myself. Sometimes it's easier to just pull up the sleeves and do the legwork. So here is the list of all of the map files with the width and height and the border block. So now we can just loop through this list, load all of the files one by one, and assemble a huge table of maps. And yeah, we get to do that with modern computers. We get to just load in all of the maps at once. This wasn't really possible back in the days on the Game Boys. We've come a long way. I decided to also save the map name and also the map index in their own properties because they might come in handy later. And I called the big table that contains all of our maps, maps. Yes, my creativity is bottomless. And yeah, now in the draw function, we can just grab one of those maps from this map table and we can just draw it to the screen like this. We can even respond to button presses in the update function to let us cycle through the different maps. But if we do that, something strange happens. We get an error. Something isn't quite right. I'm honestly not quite sure what is happening. It seems like maybe some maps are missing blocks. We can make our block drawing function a little bit more robust like this. And this allows us to browse through the maps like we want it. It seems like most of the maps are, broadly speaking, fine. If you scroll around a little bit, you'll see that for some maps, sometimes at the very end, just a few blocks are missing. So let's fix those maps during loading by filling the missing blocks with the default border block. And this is what the results look like. Oh yeah, and by the way, I haven't mentioned this, but I'm actually drawing the name of the current map and the number of the current map to the screen just so we know what we're looking at. All right, so all of the maps are loaded. We need one last thing. We need all this data to stitch Kanto together. This information is stored in separate header files, and this time around, we are going to parse those files. First, I'm going to create a new folder in our RAM called PK Headers. And then I'm going to drop in all of our header files into this folder. Again, if you did things correctly, this should be 34 files. Now, full disclosure, for this next part, I tried ChatGPT. Parsing files and converting one format of data into another is exactly that kind of menial task that AI is supposed to help out with so us developers can focus on the important things. That's the narrative that we are being sold, right? So I decided to try it out. How did it go? Poorly. First, ChatGPT tried to use functions that aren't even part of Pico-8, that are just default Lua functions, even though I specifically said I needed Pico-8 code. I caught it and I pointed it out, and then it corrected itself. But then it wrote a trim function that wasn't actually trimming out tabs. And so the first error created code that just wouldn't run at all, that would be a no starter. And later the second error created a code that would result nothing, that would return no data. Both of these would be super hard to fix if I didn't know exactly what I'm doing. As I'm recording this, just recently, Epic Games CEO Ted Sweeney said that text to GTA is what's coming next for AI. My dear man, I wrote a single function. I had to hand-hold ChatGPT all the way through it. Despite what the CEOs want you to think, ChatGPT is still struggling to compete with the rubber ducky. Anyways, here's the two functions that I ended up with, and let me walk you through what is actually happening here. Parse header accepts the text of the file as a string. It splits the file into a table where each entry is a line. Yeah, this N, that's a line break character. And then it loops through all of those lines, and it looks for lines that begin with the word connection. When it finds such a line, it takes the rest of the line after that word, and it splits all of the parameters by the comma into another table. It extracts the actual direction, north, west, east, or south. It extracts the name of the map, and it extracts the offset variable. And then here, all of this information is put into a return object. So the properties are going to be N, S, E, and W for the cardinal directions, and N off, S off, E off, and VOF for the offsets. And as you can see, this is the trim function I was talking about. Before you process a file, you kind of want to remove the indentation, and this is what this function is doing. I had to fix it so it also trims out the tabs. So now we can use this function to load in a header file and use the return object as the starting point for our map object. And then we can make sure that all the data was parsed correctly by printing out all of the information about the neighbors and exits for each map to the screen like this. And yes, if we run this, all of the connections show up wonderful. All right, we're almost ready to send things over to Pico-8. I want to change one last thing though. I don't like how the map references in here are text. For those connections, I always want to actually look up the index of the map in our table. I want this to be a number. And also for all the missing connections that we don't have, I want to fill in those with zeros. And the way to do this is to do a processing loop like this. So now we loop through all of the maps. Whenever we find a neighbor, we replace it. We look up what number that map is and replace it with that number. And for all those instances where there is no neighbor, we just insert a 0. And we do the same thing with offsets. Whenever there is no offset, we replace it with a 0. And yes, if you run this, we now see beautiful numbers. Each map now has always 4 neighbors. There's always 8 numbers associated with those maps. There is one exception though, and it's this. It's Route 22. It seems to be connected to Route 23, which is still a text. For some reason in the source files, Route 22 is connected to Route 23 in the north, despite there being no physical connection between those two maps. Route 23 is actually the road to Indigo Plateau, and you access this by going through this door and entering the Pokemon League reception. So it makes no sense that these are set up as neighbors, and in fact there's a comment in the source file that points this out. But most importantly, we want to skip Route 23 because it uses a different tile set and a different block set. That's why it's one of those maps that I haven't included earlier. So when we do the processing, I'm going to make sure that if the connection is Route 23, I'm going to zero it out as well. And this is the result we want. All right, so now we finally loaded in all of the data in one place, we verified that it works, and we fixed all of the glitches. Now we want to get in all of this data into the tiny Fantasy Console Pico-8.
Importing Kanto in Pico-8.
The problem is that Pico-8 cannot load binary files like we just did here, but we could copy the data as binary strings directly into the code. Just copy and paste it over, right? Even better, Pico-8 can include files, which basically means that every time you run a card, a file gets copy and pasted into the code. So we can encode all of this data into binary strings, export them into a file, and then include that file in Pico-8. First, a little proof of concept. This line of code creates a string that is itself a line of code, codeception. It writes that string into a file on the Picotron desktop. I save this, I run this, and now you see this file showing up on the desktop. If I open this, you see our text inside here. We moved the file to the folder of Pico-8, and now we can include this file like this, and we can print this test variable that was declared in this text like this. Nice. I wanted to point out that the export code includes this variable here, the debug variable, that just keeps track of special events that might have happened during export, just so we know what happened. It gets printed onto the screen down below here. So now that we know that this works, we can now, instead of writing hello world, we can write the entire contents of the block set file into this text file that gets included in Pico-8. There is just one small issue. This text here that we have here, this included a quotation mark. And in order to prevent Picotron from interpreting that mark as the end of the strings, we had to put a slash in front of it. This is called escaping a character. We need to escape certain characters so our programming environment doesn't interpret them and messes up the code. This is something that could potentially happen in a binary file. It's just random characters, and some of those characters might end up being quotes, or something even more disastrous. So we need to escape the entire binary string. Luckily, there is a function for that. A while ago, Pico-8's creator Zep posted this neat little piece of code in a thread on Lexoloffle. It's a function that automatically scans a string for problematic characters and escapes them. We can just drop this straight into our code. Bam! We just had to add this piece of code. You see, the initial function was meant for copying and pasting code, but now we are exporting this to a text file, and there's one character that is no problem when you copy and paste it, but is a problem if you go through a file route, and that's character number 26. That character can sometimes mark the end of a file, and the way to deal with this character is to add this line of code here. Shout outs to GPI from the Lexoloffle forums for helping out with this one. Alright, so let's see if we can use this function to escape the entire block set file and put it into the text file on the desktop. We save, we run, and it exported 2048 bytes. And on Pico-8's side, we copy over the file, we include it into our card, we save, we run this, and yes, it worked. It imported 2048 bytes. Nice. Now let's see if we can actually draw a block to the screen in Pico-8. Now I'm actually going to export this again, but I'm going to rename this variable into block data so we can reuse the same code. Picotron and Pico-8 are compatible, so we can just copy the code that reads in the block data, and we're going to copy this over into Pico-8. Something like this. And we are also going to need the draw block function. Boop. But we are also going to need the tiles, so we can just drag and drop the entire tile set into the Pico-8 graphics editor like this. And I dragged it a little bit further down so it starts at tile number 32, because this tile here, the mark with the cross, that shows up as transparent if it ever ends up in the map. So I like to avoid putting anything that belongs on the map on this tile unless I want it to be transparent. Instead, in this upper portion, I can just drag and drop in some of the graphics that are required for later on when we draw the character. Now back to the code, we can create a simple loop to loop through a bunch of blocks and draw it into the screen like this. We're going to save this, we're going to run this. We end up with gibberish because we forgot one important thing. Our tiles begin further down. The first tile is now 32. So when we draw our block here, we just need to add 32 to the sprite number like this. And here are our blocks. It just works like that. All right, let us deal with the map data next. And that is going to be a little bit more complicated because the map data doesn't exist already as a binary string. But it is possible for us to encode all this data into a single string. We can just loop through all of our maps and encode all of the properties of each map into one big string called map data. And when it gets to the actual blocks, we're also going to encode them into a binary string, but we're going to put them into a separate binary string called map blocks. I ran into some difficulties when I tried to put all of our eggs into one basket, so I'm keeping them separate. There is just two caveats here that we need to pay attention to. One has to do with offset values. The offset values can be negative, and that doesn't encode well into a byte. So before I write all of the properties of a map into our binary string, I actually loop through all of the offsets and I add 128 to each number, so all of the negative values values turn into something positive. I just need to remember to undo this later on when I'm in Pico-8. Another problem is that the names don't encode into a binary string. Obviously, they are text. So I put them all together into a one big comma separated string called map names, and I put them also into our file. Oh, and by the way, I just noticed a little bug here. Let's fix that real quick. That looks a lot better now. So if we save this and if we run this, we should have 10,035 bytes of just the block data written to our file. Let's see if we can receive this in Pico-8. And once again, we can actually use a lot of the code that we already have in Picotron as a template to write the function to unpack this binary string. This time I'm using a while loop to loop through the map data without having to hard code how many maps there are. I'm using just variables I and j to keep track of where we are in both of those strings, in the map data string and in the map block string. And yes, I also remember to subtract 128 from the offset values. Oh, and in the beginning here, I split the map names into a table of strings and I put those into the name property of each map object. And I also remember to write in the index property as well. If we run this, bam, we got a 10,035 bytes, the same amount of bytes that we wrote, and we imported 34 maps. But can we draw Palette Town to the screen? Of course we can. Again, the code from Picotron just copies over. We save this, we run this, and we did it. All of Kanto is now in a single Pico-8 card. What did it cost us?
Everything.
No, not at all. Look at this. We are only at 283 tokens, and we're about a third way in on the compressed size. There's plenty of room for activities. And that's great news, because we aren't done yet.
Putting Kanto back together.
You see, we have loaded the map data into our Pico-8 card, but this is not Kanto. This is just a map viewer. We haven't stitched the map together into one big map, and we can't walk around in it yet. So let's try to do exactly what Pokémon is doing, and let's turn this data into one big open world. Just as a reminder, let's step again through the process of how Pokémon scrolls when you walk. Again, if we look at the background map in the VRAM viewer, we see that the game has painted exactly in the tiles required to fill the screen. As soon as we take a step, for example to the right, we see a thin strip of tiles being painted in on the right side. The game then slowly scrolls the viewport over to show those new tiles. If we walk around, this happens continuously, and one of the neat reasons why this works, again, because the VRAM wraps around. So when we reach the edge of the background map, we just show the tiles on the other side of the background map. So whatever direction you're going, you can just keep writing tiles into VRAM and scrolling to the new area. We can use Pico-8's built-in map system to recreate this behavior. Pico-8's map is also just like a big grid where we can paint in tiles. And we can also scroll it with pixel-perfect precision. The one thing that this map lacks is the wraparound feature. So we need to add one more step to this process. After we completed scrolling, we need to reset the map. We move all of the tiles on the map one stack backwards and snap back the viewport to its original position. This will happen instantaneously, so the player will never notice. But this will ensure that the viewport never hits the edge of the map. To pull off this system, we need one key function in our code. We need to draw the map backwards. You see, right now we're just looping through all of the map data and we're just drawing the blocks in the map data one by one whenever they go. But for the scrolling system, we need to reverse this process. We will start at a certain x and y coordinate of the map, and we need to figure out what tile belongs to this coordinate. We need to go through all of the blocks and then look up the tiles that belong to a block to find which tile belongs there. As we will see in a second, this kind of function will become the key, the core technology required to stitch all of the maps together. And here is our first go at this kind of function. GetTile accepts a map object and two coordinates. First, we divide the map coordinates by 4 to get the coordinate of the block that belongs to the tile that we're looking up. Here's a check where we make sure that we're actually on the map. If the coordinate is an off-map coordinate, if we're looking at a tile outside of the map, then we just return the number of the border block, the block that's supposed to fill the outside of the map. Otherwise, we use the coordinates and this formula to grab the correct block number from our map. Next, if the block is valid, we need to find out which of the tiles of the block is the one that we're interested in. And the formula to find out the coordinate within the block is actually, funny enough, the same type of formula that we use above. Except instead of dividing, we do a modulo 4. We divide and take the remainder. And yeah, it took a little bit of a trial and error to figure this all out, but I like how neat the formula ends up being in the end. So this gets us the coordinate of the tile within the block. And now we use a similar formula that we used here to grab the correct tile from the block table. The little typo here is supposed to be BYR and BXR. There we go. To test this, we can loop through a bunch of tiles and just draw them to the screen. We just need to remember to add the 31 here because the tiles are a little bit further down on the tile map. And yeah, if you run this, it looks the same as it looked before, but now it's being drawn differently to the screen, and you can tell the difference if we change some things. For example, we can draw only a partial map like this. Or if we offset things quite a bit, you see that those endless fields of tall grass appear outside of Pallet Town. So let us start utilizing Pico-8's map system for our plan. I'm going to use this getTile function not to just draw stuff directly to the screen, but to instead populate Pico-8's map system with those tiles. That way, all we need to do in the draw function is just to draw this map to the screen. Okay, so for this next step, we need to do some layout planning. Hear me out. Pico-8's screen is 128 times 128 pixels in size. This is exactly 16 times 16 tiles. And this translates to 8 times 8 squares. But wait, the player's character is supposed to be smack in the middle of the screen. So if we shift the layout, we end up with a half square edge all around the circumference of the screen. If we count those partial squares as full squares, the actual area that we need to draw is actually 9 times 9 squares. And then on top of that, we need to add an additional square to have room for scrolling. So the overall area that we will be dealing with is 11 times 11 squares. 22 tiles squared. This also means that we have to shift the viewport down a little bit. We need to start drawing the map 24 pixels to the left and up. This gives us the ability to scroll up or to the left if we need to. So the map drawing function will look a little bit differently. It will look something like this: 24 pixels to the left and 24 pixels up. And this is the result. Now you can see there is a bit of a black space, and in fact we see those flowers that I drew just earlier. We aren't updating the map properly anymore, so let's fix that. In fact, let's put all of the map update stuff in its own function. So in this function, I'm actually already assuming that the current map is stored in a variable, and that variable is called curmap. And initially we set this variable up here in the init function. And here's where we fill the actual screen with tiles. The area starts at coordinates 3, 3, and it's 16 tiles across and 16 tiles tall. If we save this and run this, this gives us our palette town. Now it fills the screen. Wonderful. Now, as I said, I don't like drawing half squares, so I'm going to expand this a little bit. I'm going to fill the map a little bit more than we have to, so I'm not drawing half squares. It is time to finally put our character on the screen. And this is actually delightfully easy. We just need to draw the sprite smack in the middle of the screen like this. Just SPR 0 on this coordinate, and 2 tiles across and 2 tiles tall. And there he is. Okay, we do need to remember to make the pink color transparent and the black color non-transparent. And here is our little guy. Okay, so now we're just standing randomly in the middle of this doorway to this house. I don't like that. And in fact, we want to be moving around eventually, right? So let's track the position of the player in a set of variables. And since every step is a full square, I actually want to track the position of the player in squares. 5, 6 should be the place just in front of the doorway of our house. But how can we we move the player to that position? Let's think this through. Usually, you would think that the coordinates of a player moves a sprite around on the screen, right? This is how it worked in a previous video when I showed you how to do Zelda-style movement. But despite those games looking similarly, this is not how it works in Pokémon. As I said, in Pokémon, the player is always dead center on the screen. What is moving is actually the map underneath the player. Let me repeat this because this is so strange. We aren't moving the player, we are moving the world. Now, this is what it means for our code. We don't want actually our player's position to be affecting the position of the sprite. We want it to be affecting the position of the map. Or more specifically, the function that we just made, the function that fills the map with the tiles. In here, we can take this little formula, which will take the position of the player, and it will calculate the map coordinate of the top left corner on the screen based off the position of the player. And now all we need to do is to make sure that when we're filling in the map, we're starting at that position rather than at 0. Just want to make sure that the player position is defined before we actually fill the map. And if we run this, this is what we wanted. This starts us out in front of the door. Now, if we just add some basic code to change the player's position depending on button presses, we can start walking around on the map. And if you watch my previous video, this will look very familiar. This is very straightforward code. And look at this, we can walk around in Pallet Town now. Isn't this sick? Isn't this crazy? We can even go into the crazy, creepy area where the tall grass is. Yes. Now, one important thing to keep in mind is that after you press a button, you absolutely want to refresh the map by filling it with tiles. By the way, here's a little detail that I love that Pokemon does to make things look a little bit nicer. Right now, we're drawing the player sprite aligned perfectly to the grid. It's aligned with the tiles. That is not quite how it works in Pokemon. In Pokemon, the player sprite is shifted by 4 pixels upward. That way, whatever is above the player gets overlapped by the player's sprite, and it looks a little bit as if it's behind him. It's such a cheap little trick to lend a bit of a sense of perspective. I love this. Alright, we're making huge progress here, but there's 2 major features we need to wrap things up. First, we need to stitch the map together. We need to create this big open world, right? Second, we need to pull off that Wallace and Gromit scrolling trick. Let us do the stitching first. As I mentioned, the getTile function is the key to pull it off. Here's how. We have this part here where when we're requesting a tile that is off map, we're just printing out the border block. We can expand this to do the stitching for us. Let's say we are requesting a tile that is in the north of the current map. We can then check if there's supposed to be a map attached onto the north side, and if that's the case, we can start filling in the blocks from that map instead of the border block. And so once again, here's how the code works. So if we notice that we're in the north and there is supposed to be a north map, we get that map from our map list, and then the function getTile calls itself recursively. We call getTile from within getTile, but instead now we're looking into tiles of this new map in the north. The only tricky thing is really just to adjust the coordinates. First, we need to apply the offset of this north map to the X position, and then we need to shift the Y position by the height of the map in the north, because we are moving one map over. We want to be operating in the coordinate system of that other map now. And yeah, here we go. Route 1 now correctly attaches to Pallet Town. Isn't this neat? Now we can repeat this process for the other 3 cardinal directions, and it works the same way. And yes, this looks very dense, but it is essentially the same code just repeated 3 times with just small adjustments. For the west and east direction, the offset is applied not to the X coordinate, but to the Y coordinate, like here. And for the other coordinate, when you're going south and east, you need to add the width or height of the current map, not the next map. But otherwise, we're peachy. We can just walk around and we can move into Route 1. And the crazy thing is that we can continue going all the way to Viridian City and beyond. The entire map is suddenly accessible to us. Crazy. Now, I have to say, this is a little bit cursed, and we're gonna see what's happening when we write the name of the current map and our current position to the screen, like so. So you see, when we walk off map, we're now in Route 1, but the game still thinks we are in Pallet Town, just extremely mainly off-map. It just became so good at filling in all those off-map values that we can actually walk around in the entire Kanto region. But this is a little bit sketchy, so let's add a set of similar if statements after we move to make sure that if we move off-map, we switch the current map to the map that we're currently on. And just like that, open world achieved. Yes, we can traverse the entire Kanto map like this. Yes, the game would always switch to the next map, allowing us to traverse to all of those maps, and it will stitch them perfectly together. It all happens seamlessly, an illusion of one continuous map. Okay, I use the term seamlessly, but maybe seamlessly is the wrong term here. The movement is still quite jerky. We aren't actually using this Wallace and Gromit trick I talked about before. We just redraw the entire screen on every step. So let's finally implement proper scrolling.
Walking in Kanto.
First, this code is getting too long, so I'm gonna reorganize things a little bit. I set up dedicated tabs for the draw functions, for the update functions, and a dedicated tab for all of the map updating stuff. And then I just move all of the functions that we already have in the tabs that they belong to. Now, if you watched the previous video, you probably already know what it takes to make such jerky movements smooth. Yes, we have to set up a state machine, which just means the game will do different things depending on which kind of mode we're in. In the mode idle, we're just gonna call this function called checkbuts that will just respond to button presses. In the mode walk, we're just gonna do the walking and the smooth scrolling. Now, I'm not gonna explain every single line of the system. I already did a very long video about how that works. However, here are the most important points. So we don't immediately change the position of the player anymore. Now we have those next X and next Y variables to store where we're about to walk to. We also added a set of variables to control how much the viewport has scrolled. And we're adding those variables to where we draw the map. And we also set up a set of variables that control the speed at which the viewport is moving, SDX and SDY. We set them when we press a button, and we apply them in this function called movePlayer. This function gets executed when we are in the walking mode. The speed at which we are scrolling is going to be 1, that is 1 pixel per frame. That's generally the speed I see when I look at footage of Pokémon Gen 1. So when we press the button, we set the mode to walk, and we also add a variable called dist. This tracks how long we are going to be scrolling. Every frame movePlayer gets called, we apply the speed, the velocity of the scrolling, and when the distance reaches 0, the next position becomes the current player's position, and we do this big check where we check if we walked off map and switch to the next map if we do, and then at the end we reset our scroll values back down to 0. We fill the screen with new tiles for now, this will change in a second, and then we reset the mode to idle and wait for more button inputs. One little detail, these are not supposed to be BTNP anymore, these are supposed to be just BTN. And yeah, even with a pretty rudimentary system like this, we get pretty good scrolling already. Of course, now when we walk, we always get those glimpses of the bits of the map that haven't been filled in. Time to engage Wallace and Gromit mode. But since we already did all this prep work, it's as easy as filling in those thin slices of the map with the fill map function. And we do that every time we press a button. And to be fair, figuring out the exact numbers that we need to put in here can be a little bit tricky, but referring back to the planning, to the layout planning that we did before, can help a lot here. And yeah, this looks wonderful. Okay, so this is actually 100% usable, and it's fine to leave it like this. However, I want to point out that we are cheating a little bit, because after each step, we just fill the entire map with tiles. We just reset the map whenever we do a step. This is a bit of a brute force approach. And yeah, you can see every time we take a step, you can see the CPU taking a little bit of a blip because it takes some time to refill the map. Now, this is fine for a system like this. This doesn't bog down the system in any way. However, I thought maybe I'm going to write a small function that does things a little bit more in the spirit of how it would maybe work on the Game Boy. Instead of refilling the map, I just want to write a function that just shifts the content of the map that's already there by a single square. Just to visualize what the goal is, we can remove this step where we refresh the map, and now when we take a step, it resets back to where we were. In order to make the scrolling stick, we have to shift the entire map one step after we take a step. So this first naive solution is pretty straightforward. We just loop through the entire map, we save the tile numbers in a table, And then we loop again, and you write the tile numbers from the table back into the map into a new position. But now we're looping through the map twice, and kind of like the little problem that we get, the little CPU blip, got actually a lot worse. So this is probably not the way. It's way easier to just refresh the map. So I ended up doing something that's a little bit more advanced. In this version, I'm directly manipulating the memory that encodes the map data. This lets me efficiently move a large amount of tiles in a blink of an eye just using the function memcopy. And yeah, there's still a small CPU blip, but it's minimal, and this works very, very nice. Okay, I know what you're thinking. This looks weird that our character is just hovering in place like this, so let's add character animations. From here, it should be familiar ground if you watch my previous video. I just set up a table with animation sequences for all of the 4 walking directions. I also set up 2 variables to keep track of the progress of the animation and a third variable to keep track of the walking direction. Now, some of the animations actually require flipping the entire sprite. So I set up a dedicated function responsible for drawing the player's sprite. And I set up a system that if the number in an animation table is negative, it grabs the sprite but also flips it. As you can see, some of those numbers in here are negative. I put this little bit of code in the move player function to progress the animation as the player is walking. We want to see a new animation frame every 8 game frames. And in the check buttons function, I make sure that we remember which button was pressed. And if no button was pressed, I reset the animation to a default value. And check this out. Doesn't this look exactly like Pokémon Gen 1? Now, of course, at this point, we have 0 collision detection with anything on the screen. We have fully enabled a no clip mode. So this might be a good opportunity to see if all of the techniques from the Zelda videos to enable collisions with tiles also work on a complex system like this.
A collision with Kanto.
So the way this works in Pokémon Gen 1, in those games, the collision check is always performed on the bottom left tile of each square. I went a little bit overboard and simply marked all of these tiles as unwalkable by setting for all those tiles flag 0, which is the red light. And then in a checkbox function, we can simply use our getTile function to sample the bottom left tile of the square that we're about to walk into. And we only allow walking if flag 0 for this tile has not been set. And look at this, it's beautiful. It starts to feel like a real game with, rules and consequences. But oh no, since we disabled our no clip cheat, we inevitably made a lot of areas in our Kanto map completely inaccessible. Guess we have no choice than to implement a few additional movement mechanics. First and foremost, one cool and in my opinion underrated feature in a lot of Pokemon games are those one-way ledges you can jump down from. The character can jump over these but only going one way. Going the other way they will stop you. However, those ledges are currently inaccessible in either direction. Let's fix that. Again, we just need to set some flags on some of the tiles to mark which ledges are jumpable from which direction. I'll set the orange flag, flag number 1 for those tiles. These represent the ledges for jumping down. The yellow flag, flag number 2, is set for those 2 tiles. They represent the ledges where you can jump to the right. Now this can be a little bit confusing because those tiles look actually empty. But if you look closely, those tiles are used exclusively on squares that have the ledge where you can jump to the right. And finally, the green flag, flag number 3, is set on tiles that paint the ledges where you are allowed to jump to the left. Now, the big trick with the ledges is that essentially whenever we jump down from a ledge, we're just taking 2 steps in a row. However, taking steps is currently tied up to pressing buttons. So I create a dedicated walk preparation function that sets all those variables required to do a step, and I call this walk prep. So now I can do steps independently of button presses. And then the actual jump is similar to the way we do collision detection. If the walking direction and the flag of the tile that we're about to walk onto match, we just do a normal step, except we set a special jump variable to indicate that we're supposed to do 2 steps in a row. And yeah, this technically works. It just doesn't quite look like a jump, right? No problem. All a jump is just moving the player's sprite up a little bit. Here, check this out. We set up a fly and fly speed variable, like so. We use the fly variable to potentially draw the player's sprite a little bit higher up. This is basically going to be our altitude. And when we are in the air, we also want to draw a black round shadow underneath the player. On the start of the jump, we set up the fly speed variable to some kind of value to catapult us in the air. 1.6 seems fine. And in the function move player, where we actually move the player, we can also apply the flight speed to our altitude. And also additionally, every frame we decrease the flight speed until it turns negative and we fall back down to Earth. To prevent the altitude from dropping below 0, we use a little max function here, and also we lock the animation frame to 2 so we don't move our feet while we are in the air. Now I also added a small sound effect, and look at this. Oh yeah. This looks nice, doesn't it? Yeah. Now this seems like it would make a lot of the map a lot more accessible, but we need to walk only as far as Route 2 to encounter another obstacle. Now this door leads to Viridian Forest. Viridian Forest is a new map that uses new tile set and new block set. I would prefer not to import it. Instead, it would be great if walking through this door would put you at the exit of Viridian Forest. This is actually super easy. We just need to set up a table which encodes which location should teleport you to which other location. Look at this. Let's say map number 1, which is Pallet Town, and then the location 1211, which is the door to Professor Oak's lab. Let's say that teleported us to map number 2, which is Viridian Town, and then the location 2325, which is the Pokemon Center. And then I do a little bit of a note here, pointing downwards, meaning that after we warp, I want to do a step downwards, so it looks as if we're walking out of the door. Then I write a small warp to function, which basically sets a player's position, it changes the map, updates the background tiles, and also does a walk if required. And now after each step we take, we just loop through this list of warps and we check if our current position and map number, that's where we use the index, matches one of the entries in the warp list. And if so, we just run the warp to function. And there is a little of a cheeky use of unpack to dump the warp table data directly into the function as parameters. And one little bug fix, we need to add a return here. And this should be an MX, and look at this. We can now walk through Professor Oak's door and it teleports us to Viridian Town. Now, if you're like me and this transition is a little bit too sudden for you, we can add a small fade to make this all nice and juicy. I personally love Comet Bomb's fade generator. I set the fade length to 4 steps, which gives you this Game Boy look, and I set the target color to white because I want the fading to turn into white. Now this generates some code. We have to put it in our cart, and we maybe have to adapt it a little bit so it works with what we have. But when you do, you end up with something like this. Ah, wonderful, isn't it? Alright, okay, but in real Kanto, Oak's lab isn't a magical portal into Viridian Town. In fact, there's dozens of caves and gates everywhere, and so now begins the arduous process of walking through the entire map, writing down the locations of, where there's supposed to be a portal. And yes, this just takes a while, but at the end you end up with a huge list like this. Bam! And yes, this is extremely token inefficient. If this was a real game, I would be probably interested in encoding this, for example, into a binary string like we did with all of the other data. After all, it's all just numbers, right? But for now, I want to keep it like this because it allows us to modify the data in case we want to change something. I also want to mention that this is essentially how all of the interiors of the buildings and caves work in the real Pokemon game. Each map has just a list of locations that teleport you from one place to another. And sometimes those locations will be other maps. Walking onto a door will teleport you to a map that shows you the interior of that building. Walking on the stair will teleport you to another map that shows you a different floor. The only difference is that we just have this huge gigantic list, whereas in the Game Boy version there is a separate list for every map. Now, scouting out all of those locations can be quite time consuming. It takes a while to get to some of those locations. Fortunately, we can actually use the warp to function to start us out immediately at a certain place. For example, if I just want to start out in Viridian City, I can just write something like this at the beginning of our code. And yes, this starts us out in Viridian City, and we can check right away if the Viridian Forest warp works. And yes, all of those warps also work now. Of course, I've been a little bit extra and I added this handy fast travel menu that allows you to quickly teleport to different towns in the game. And here's how it works. All the way back in March 2021, Pico-8 introduced the custom font feature. And back then, to show off this feature, I actually recreated the Pokemon font in Pico-8 when I made the video. Well, it's time to bring out this old chestnut. Now, I did some tweaks. I did add those few special characters in here to draw the border. And if you run this card, it exports a special string into the clipboard. And then you can paste it into your card like this. And then you can use it to print stuff on the screen somewhat like this. And check this out. Hello World with the Pokemon font. So now we can use a whole bunch of simple print statements to draw a whole menu just like this. Yeah, that's what I'm doing here. I'm just drawing a whole bunch of lines of text. And then I set up a whole bunch of tables in an init function for all of the names of the towns. I have 2 pages set up here. I have a whole bunch of variables to keep track of the location of the cursor and so forth. And then this table is just the warp locations for the different entries in the menu. And then in an update function, we set up a separate menu mode that will respond to button presses differently. It will change the cursor and activate the different options in the menu. And it looks like this. I'm glossing over this because this is generally not remarkable code. Now, what is actually remarkable here is how big and clunky this text is. Yeah, on the Game Boy, you had to use sprites to write out individual letters, so each letter had to be 8 × 8 pixels in size. It's shocking how hard it is to fit any meaningful text on this screen like this. Even I had to split the list of all of the towns into 2 pages because they wouldn't fit on a single screen. After building this menu, I went back in and looked at all the screenshots from all of the menus in this game. I'm so impressed how effortlessly functional they all are despite of the harsh limitations they were created in. It takes a special madman to look at a system that can fit like maybe 18 characters in a line and say, yeah, let's do a sprawling RPG in this. Anyway, back to our recreation. So when we teleport to Viridian Forest, we can encounter an obstacle that is quite infamous. These plants here. Yes, this is a famous plant that can be cut down in the game using the HM cut. And as long as you don't have the HM cut, it will block your progress in a lot of places. Well, it blocks our progress now, so let's implement the cut HM. This is actually pretty easy to do. We once again have to mark a bunch of tiles with a flag. This time we're going to use flag number 5. And then when we're about to collide with it, we just do some cutting instead. And the actual cutting is a little bit inefficient. I'm just setting each individual tile of the square to a different tile. The only difficulty really here is to calculate back from the player's position back to the sprite on the screen on Pico-8's map. And we do this here in those 2 lines. Now, if we do this, the plant will disappear, but we can't walk there. It just plays the sound effect over and over again. That is because when we're doing collision detection, we aren't actually checking the actual tiles on the screen. We are looking into our data structure using the getTile function to figure out what tile is supposed to go in this place. And it's an easy fix. We need to just sample the actual tile from Pico-8's map. And yeah, now we can cut down those plants no problem. Now, again, this is a little bit sudden. This is not how it looks in the game, so we can spice this up a little bit. And again, I'm going to gloss a little bit over this. I'm just going to add a new mode that is going to be the cut mode that will play a small cut animation. And the actual cut function looks like this. Is very simple. We're just running this every frame. We're just progressing a timer, progressing some variables, and after 10 frames, we're switching back to idle. And this is how we draw this animation, basically drawing 2 sprites, which are the 2 halves of the plant, and then moving them aside. And there is a little bit of a blinking happening here using a modulo and the timer that we have here. And now in our cut function, we just need to initiate this new mode and set some variables. So the sprite of the tree appears where the tree was previously before it disappeared. And this is what it looks like. Yeah, that's pretty sick. Now, something I like about this specific implementation of the cut is that when you walk away from this, and then walk back, you see that the tree regrows. And that's because of our Wallace and Gromit system. This space where the plant was remains empty while it's still on the screen, but once it moves off screen and then reappears, our Wallace and Gromit system draws in the tree that's supposed to be in there, so it looks as if it respawns. This is kind of how it works in a real game, except in a real game, the trees don't respawn until you leave the entire map. This suggests to me that on the Game Boy they keep a copy of the entire map in memory. My guess is that they're saving the blocks, and when you do the cut, you don't actually change an individual tile, you change out the entire block. But that's just a guess, don't quote me on this. Anyway, the only thing that is stopping us from traveling all across Kanto is the water. Except not really, because we can just walk over the water. We never set it as something that stops us. So we can do the Pokemon Jesus here. Yeah, it looks a little bit goofy, I know. In the real game, you can't travel over the water, but you use the surf ability and you use this different sprite that looks like, I don't know, dugong or seal. And sure, we can also implement that real quick. It's actually really easy. First, let us paste in the missing sprites. Then we set up a second table with new sets of animations for the surfing. We mark all of the water and water shore tiles with flag number 6, that is a pink flag. And then in the checkbox function, when we do the walk, we just set a variable depending on whether the tile we're about to walk onto has this flag set or not. And then in a function where we draw the player sprite, we just use a different table to look up the animation if the surf variable is set. And really that's all we need. Now we can walk over the water and we immediately change into this different sprite. Nice. Okay, since this was this simple, I want to do one last effect that I always found quite fascinating. I always wondered how it worked when you walk over the tall grass and half of your player sprite is kind of like embedded in the grass. Turns out it's a very simple trick. You basically split the player sprite in two halves. And then the order is like this. First, when the screen is empty, you draw just the bottom half of the player sprite. Then you draw the entire map on top of that, but you make the white color transparent. And then finally, you draw the top half of the player sprite on top of that. And here's how to pull this effect off in Pico-8. First, we mark this one tall grass tile with this flag, flag number 4, it's the blue flag. Then in the collision detection function, just like we detected where we are on the water, we can also detect if we are on the grass like this. Flag number 4. And now we just have to change a little bit how things are being drawn. First, we fill the screen with a white color, and then we can just draw the entire player sprite. Now we can actually get away with drawing the entire player sprite because the top half will get covered up anyway. Now we're gonna set the white color to transparent. We're gonna draw the map on top of that. We're gonna turn the transparent color opaque again. And then if we are in a grass, then we can just use a simple clipping rectangle to make sure that only the top half of the player sprite is drawn. Otherwise, we draw the entire player sprite. And man, somehow it feels like I needed this effect the most. Like this makes it feel really like Pokemon. I'm getting anxious that I'm about to get a random encounter. I have to admit I have so much fun with this, I could just keep going and going. I had a prototype version that had the flower animation. I even implemented a bike. But this video has been going on for a while and we achieved our goal already. All of Kanto with its mesmerizing continuous map has been implemented in Pico-8. And we even have some room to spare to build a small game. So I'm gonna put up this card on lexlevel.com and it will be available in the video description, and I'm gonna leave the rest to you. Knock yourselves out, play around with this and let me know if you have something cool. But also, heed my warning. Beware of the siren call. Resist the temptation to recreate all of Pokemon in Pico-8. Ink Golem 4 years ago. Pokemon Red and Blue never made it out of Pallet Town. Ill-Made Coder 9 years ago. Pokemon Yellow D-Make never made it out of Pallet Town. Springo-Geek also 9 years ago. Pallet Town. Well, okay, that's kind of on the nose. Yes, he also didn't make it out of Pallet Town. Don't get me wrong, I'm not making fun of my fellow devs here. On the contrary, Pokemon is such a beloved and popular series. The desire to recreate it and create your own version of it is something I understand very well. Otherwise, I wouldn't even be here. It's easy to get caught up in excitement and catastrophically underestimate how big this game actually is. We made it further than most, we have all of Kanto, and yet there is still so much more to go. 151 Pokemon with unique attacks and stats, a whole battle system, a whole Pokemon box system, dozens and dozens of NPCs with custom dialogue, cutscenes, unique events, huge interiors, all of them using new sprites and block sets. Think twice before opening this gigantic can of worms. my tip is better try to think of something new and exciting to do in this space. Perhaps a DoorDash simulator or a bike racing game. To me, this has been a fantastic exercise to understand how all the classics were made. I'm once again blown away how much Game Freak was able to achieve on such a limited system. And to me, the magic of Kanto still works even in this, diminished version without any NPCs or, Pokemon. Just being able to traverse this huge sprawling environment conjures this sense of grand adventure. Makes you wonder what else you can find and how far you can go. I learned a lot that will come in handy when I will make my own games like this, and I hope you did too. And so all that is left to do is once again thank my wonderful supporters over at Ko-fi. The response on the last video was great, and I want to give a huge shout out to all of the new supporters, including Wilbert, 16-bit Hyper Turbo, Teo Murgi, Sean. And also thank you to all of the One of the Nations by Dave, Alex, Bandage Man Studios, NNS Faka. And a very special thanks for the extra generous donation by Daddy Funk. Thank you so much, Daddy Funk. So this was a deep dive into Pokemon. I know this was a bit of a detour from the last video, but I fell down a rabbit hole and I had to tell you all about it. Rest assured, I read all of the wonderful requests on the Zelda video, and don't worry, I got you. Unless, of course, you want me to continue with some Pokemon related topics. I'd be down for that. Let me know in the comments as well. Whatever happens, it's gonna be great. And hey, happy Pokemon Day to all of you who celebrate. See you next time around, guys. Bye bye.